Okay, good. Let me see. I have a couple of students to admit. That's fine. Okay, the recording started. Again, 1 second. Okay, I can't admit the students. I don't know why. Let me see. Still cannot admit. Okay, anyway. Okay, anyway. I think you see my screen. Let me go back to the page and let's get to our link. Just wanted to remind you that we are now focusing on the estimation of climate change and climate change impact. And the purpose is to try to get information on the future the future threats, plural, that are originated by climate change. And these future threats, hopefully we can estimate in terms of probability. We know what is probability. And we are focusing on then methods for making predictions. Making predictions means that we anticipate what will be the configuration of the Earth system in the future under climate change, what temperature will be, what water resources availability will be, what river frequency of river floods and coastal flooding will be. And as you know, we focused first on inductive approaches. We discussed linear regression, for instance. We discussed round theory. We discussed also the estimation of the memory of the process. And then we are focusing on the deductive estimation. But I started with a very simple model. The very simple model is, just let me open the link, is the rational formula, which we get in this web page about here. Let's give some time and let's, okay, it's here. We go down, it's here. Okay. First, I want to find a way to put on the screen, to magnify on the screen the analytical formulas. Let's see. This is okay, but give me a second. I want to see if I can magnify it even more. So let me select the formula here. This is the first experiment that I make, and then if it works, given that I have to make other analytical development today in the morning, I want to make sure that I can visualize on the screen the formulas. Let's see. Okay, a bit better. Let me bring over the screen this one. Okay, good. So it's a little bit unfocused, but okay, good. So this is the rational formula. I said that Q is river flow, is peak river flow. I just make a brief recap. C is a parameter, a constant. I will explain to you what is the purpose of this constant. I is rainfall intensity, precipitation intensity, and A is the area of the catchment. We discussed the dimensional analysis of this formula. We demonstrated that is dimensionally correct. In particular, we said that C has dimensionless, I has the dimension of a length over time, and the area is square length. And so the right hand side is given in terms of dimensions by the ratio L cube divided length cube divided by time, which is the same dimension of the Q, the peak river flow, on the left hand side. Now, first of all, what is C? As I said, this is a conservation equation, is a conservation of mass. Conservation of mass simply says that what rains over the land, I find into the river flow. in terms of water flow, which is of course physically reasonable, physically motivated, but doesn't take into account that there are losses. Conservation equations work even if we have losses, but we have to account for them. I mean, it's fine to impose the conservation of mass of water, even if I have losses of water. Think at evaporation, it's a loss. So part of the rain, part of the precipitation evaporates, which means that I don't find that water into the river. But I can still apply a conservation equation if I plug the losses into the equation. So what is C? C is a coefficient between 0 and 1 that allows the rational formula to account for losses. For instance, if you put C equal to 0.5, it means that half of the rainfall is lost because the computation CI becomes 0.5 I, 0.5 rainfall. So if I consider as water mass input only half of the rainfall, it means that I am implying that the second half is lost, which is perfectly fine. It is a reasonable way, it's a smart way of computing losses. So the moral of the story is that C is in the range, is lying into the range 0, 1. If it is 0, you have everything lost, and therefore Q is resulting 0. If C is equal to 1, you have no losses. So it is indeed a smart way of taking into account the losses due to evaporation and other reasons which may happen. There might be also artificial reasons induced by human impact. For instance, think of water withdrawals from rivers for civil purposes. Just 1 second, I take the sweater off, just 1 second. Good, it's becoming too hot in my office. Okay, in this formula, the C opens a question mark. How can I estimate C? You understand that C is very influential on the result because it can change the result by any percentage between 0% and 100%. So the question is, how can I estimate C? C is called, by the way, runoff coefficient, and you find the description in the web page. A second question is what is the value for I, rainfall intensity, to be plugged into the rational formula? And the third question is how to estimate A. A is relatively easy because it's the area of the catchment. For the catchment is, as I said, the land, the portion of land contributing to the river flow. And very often we already know the area of the catchment. For instance, if you think the Po River at the closure, close to its mouth, the catchment, we know the value is about 70,000 square kilometers. And this is something that for most of the rivers we already know. And if we don't know it, it is relatively easy with a surveyor, with the help of a surveyor, to study over a map the extension of the catchment and get a value. So A is not a problem. It remains a problem, the estimation of the other two components. Why I am focusing on it? Because I hope that I give to you the feeling that in order to solve these questions, we rely on our understanding of the process, our understanding of how river flow is formed. So this reasoning helps us to understand that behind any empirical formula, behind any empirical formulation, there is a reasoning based on our knowledge of the Earth system. And this applies to any empirical formula that you may consider for whatever risk related to climate change. So first of all, let me focus on C. C is called, as I said, runoff coefficient. It is varying in the range 0, 1, and usually you may have an indication of the value of the runoff coefficient that can be derived from the information that you find in the website of the environmental agencies. So for instance, the Environmental Agency of the United States for some major rivers suggests the value of C. And keep in mind that we assume that C is a constant, so it's independent of the magnitude of the event. So it's independent of the return period of the event. Please be aware of the concept of return period that we introduced some time ago. When we talk about a natural hazard, earthquakes, whatever, we can talk in terms of magnitude of the event, and the magnitude is usually quantified through the return period, which is related, as you may remember, to probability. So C is assumed to be independent of the return period, while we know that actually it depends on the return period, because if you get a very extreme rainfall, the very extreme rainfall occurs when you have reduced evaporation, very low evaporation, and therefore typically you have less losses. So unfortunately, the very extreme rainfall, the very extreme storms cannot be mitigated by likewise extreme losses. We get extreme rainfall, and on the other end, the losses are minimized. So this means that C is changing depending on the return period of the event. When it becomes extreme, high return period, C tends to 1. When the event is low intensity, low return period, C is shifted towards 0. This is, of course, a limitation. We have to be aware of that. But for the additional formula, we assume that C is constant. My suggestion, if you are interested in flood risk, then it's better if you assume a value of C quite high, like 0.8. If you're interested in applying the rational formula for estimating water resources availability, then it's better to decrease the runoff coefficient, because on the one hand is more conservative. I mean, if you focus on low flows, if you want to get protected against droughts, the application of the rational formula is more conservative if you take a low value for C. And therefore, I wouldn't suggest a 0.8. I would say take 0.5, 0.4. And then we will talk later, I think later today, on more quantitative procedures for estimating model parameters. C is a parameter. So let's postpone this discussion. Now let's discuss about the value of I. What kind of rainfall intensity should I plug into the rational formula? First, we said that the rational formula in principle is conceived for estimating peak flow. So you have to put a high rainfall intensity there. A rainfall intensity that corresponds to a high return period. This is the first consideration. Second consideration, let me go to the web page at this stage. It's here. So let's focus on the part that I selected. But you can listen to my words. It's not necessary that you read. I just want to put on the screen a reference to what I'm saying. So if you look at the rational formula here, I go back to the expression of the rational formula. it can be demonstrated that if you take this kind of relationship between a river flow and rainfall, we are implicitly assuming that the return period of the two quantities, peak flow and rainfall, is the same. Okay, and this is what is stated here. So the rational formula assumes that you have the same return period. So what is the practical consequence? If you are estimated if you are interested in estimating Q for 100 years return period, then you should plug in into the rational formula a rainfall intensity with 100-year return period. This assumption is clearly not reliable. Not reliable. Why? Because it implies that the rainfall and the river flow have the same probability distribution, which is not true. It is not true because they have a completely different structure. The same rainfall may cause one day no river flow and another day may cause a flood. Because you know the proverb, it says, it rains over the wet. What does it mean? It means that if it rains the same rainfall over a dry soil, it's not a disaster. If it rains over a wet soil, it's a problem. So you understand that the same rainfall can cause two different values of river flow. So they cannot have the same probability distribution. And so this assumption of uniformity of the return period, uniformity of probability distributions, is clearly not reliable. So climate change, if it causes a change over a rainfall and the rainfall becomes more intensive, doesn't produce the same effect on the river flow everywhere. It depends on the season. So if you have a climate change, an increase of rainfall in the flood season, it's a problem. If you have an increase of rainfall in the summer season, which is not a flood season, may be good, maybe an opportunity. So this example clearly clarifies that the impact of climate change, it's not directly related to climate change itself. You have a change in climate, the impact may be markedly different depending on the season, depending on the country, depending on the location. If you have a water problem in a location that already has water problem, if you have an increase of drought risk in a location where you already have water scarcity, of course, it's a big problem. If you have a climate change in a location and a reduction of water availability in a location where they have a lot of water, it's not a problem. So this is an important example to clarify that, as I said, the impact of climate change varies, depends on the local conditions, depends on a lot of things. It's not uniform everywhere and needs to be carefully studied with an impact model. In this case, the impact model is very simple and assumes that the return period of climate change and flood change are the same. The return period of rainfall and river flow are the same. But this is a simplification. It is fine because we are aware of it and we use it in order to simplify and make more reliable, for technical reasons, our assessment. But on the other hand, it's important that we keep in mind the concept. So it's important to establish this relationship between climate change and the impact. Because in some cases, unfortunately, it may happen that even a small change in climate, even a tiny change in climate, causes a big impact. In other cases, we can afford the change in climate because the impact may be much lower, or it may also be an opportunity. We will discuss again this case of climate change becoming an opportunity. It is extremely important because when we adapt to climate change, we also have to take any occasion, any opportunity for transforming the problem into a potential benefit. Okay, let's come back to the rational formula. So we said rainfall intensity with the same return period, but there is another question related to rainfall, which is interesting because it allows you to understand how rainfall runoff modeling works. What is the duration of rainfall that I have to plug into the formula? Because rainfall events are defined depending on their probability, so return period, and duration. So when we talk about a design precipitation, a design forcing due to precipitation, we have to talk about return period and duration. Because you understand why. Rainfall may last for a long time. Typically, here in Italy, it's the fall season. You may get, recently we didn't get much, but you may get rainfall lasting for 1 week or 2 weeks. Or in the summer season, you may get rainfall events that last 5 minutes. And those that last only a few minutes are usually more intense than those that last a couple of weeks. You know that when we get these long perturbations in November, the rain is very fine. It's like fog. It's low intensity rain, which is lasting for a long time. When you get these thunderstorms in summer, in 5 minutes you get completely wet. So it means that the intensity is different. And then it means that we have indeed to specify what is the duration of the rainfall event that we plug into the rational formula. Because if we decide to plug in a short duration, then the intensity, the resulting intensity will be much higher, much higher. You can find the design rainfall for several rivers over the web. The literature proposes several examples for design rainfall depending on the return period. And you will see that the design rainfall for the Po River is a rainfall of low intensity lasting for a couple of weeks, while the design rainfall for a small creek is high intensity lasting for maybe a couple of minutes. So what is the duration of the precipitation event that I have to plug into the rational formula here? The duration is corresponds, can be demonstrated that the correct procedure is to use a rainfall with duration corresponding to the time of concentration of the catchment. What is the time of concentration? First of all, we don't demonstrate this statement which I'm delivering now. So we don't demonstrate that what is the critical duration, the suggested duration for rainfall intensity. We don't demonstrate it. If you're interested, there are several links over the web, several information over the web. But I am instead interested in specifying what is the time of concentration, because if it happens to you to talk about rivers in your professional career, the time of concentration is an essential information related to a river. So if we talk about the Po River and we have to make a design project for the Po River, the area of the catchment is the first information that we collect, but the second information is the time of concentration. So what is? There is a link here. Let's see if it works. By the way, there are several links on my web pages, as you know, and the problem of links, they are very useful. The problem of links is that sometimes they get broken. So if you see broken links, because in the morning I found a broken link indeed somewhere, if you can please tell me, I make the correction. So time of concentration, let's click over it. Okay, let's have a look and then I give you a definition in poor words. Time of concentration, it's a concept used in hydrology to measure the response of a watershed to a rain event. Definition. It is defined as the time needed for water to flow from the most remote point in a watershed to the watershed outlet. Okay. It's the travel time of water through the catchment. And here it says it is a function of the topography, geology, and land use. A number of methods can be used to calculate the time of concentration. Okay, we don't take more details. These methods are essentially empirical formulas. But let's forget about the details. It is just enough that we know that there are empirical formulas, very simple application, which allows us to estimate this time of concentration. So again, what is the time of concentration? It's the travel time taken by a drop of water that falls in the most remote location of the catchment to flow up down to the catchment outlet. It's the travel time of the most remote drop to get into the river at the outlet. The concept, I think, is clear. So you understand that for the Po River is much longer than for a creek. Indeed, the time of concentration of the Po River may be 10 days, a couple of weeks. For a small creek, the time of concentration is probably a couple of minutes. And this explains why for a small creek, I need to consider a short time rainfall. For the Po River, I need to consider a rainfall that lasts for a couple of weeks. Good. Okay, so let's go back to the rational formula then. And 1 second, I need to go back to the web page first. Perfect. So I think we cleared everything up. There is one last thing that I want to say for rainfall. Rainfall should be an average value over the catchment. And therefore, this is a little bit of a complication because if I need to compute the average rainfall over the area, the average rainfall is lower than a point rainfall, a point extreme rainfall. It's lower because the distribution of rainfall is not homogeneous in space. So there are empirical formulations that allow you to take into account this reduction factor of rainfall. But again, this is another detail we don't want to focus on. It's not important because these are all very simple details. But there is instead a consideration that I want to elaborate with you, with the hope to also give you the feeling of the connection, a better feeling of the connection between an empirical formula like the rational formula and the physics, the dynamics of the process of the Earth system. If you think about a formula like the rational formula, we already said that there is a physical basis. It's a mass balance. Very good. On the other hand, you understand that if you want to describe a flow, Q is a flow. It's a river flow. If you want to describe the flow of matter, flow means movement, means matter that is moving. You are not only describing the mass of the matter, but you are describing a connection with the move of the matter. So if you think at it, it's clear that from a physical point of view, the mass balance equation is not enough to describe flow. You need also to include an energetic component. You need to include a conservation of energy. Because I state again, I repeat the concept. If I only want to describe the mass, then it's fine to resort to the mass balance equation only. But if I want to describe flow, I need to consider energy because the flow occurs at the expense of energy. Flow needs energy. So it is not possible that a relationship like the rational formula ignores the energy balance. So this reasoning brings us to wonder, to ask ourselves, where is energy balance in the rational formula? Where is energy balance? We said we already identified where is mass balance here, because it is clear, no? A rainfall over the catchment and then mass of water flowing. But on the other hand, where is the energy balance here? It must be somewhere, okay? So it is not for sure in the area of the catchment. It's not for sure in the runoff coefficient. It can only be in the rainfall intensity. And in which form the energy balance is impacting the rainfall intensity? It is connected in some way to the rainfall intensity. The energy balance is connected in some way to the rainfall intensity through the rainfall duration. When we say that the rainfall duration must have a duration that is equal to the time of concentration, basically, what does this mean? It means that the time of concentration is related to energy. The time of concentration, I said, it's a travel time of a drop of water. So I am considering through the time of concentration this flow component, this energy component. And when I say I need to put into the rational formula a rainfall intensity with a given time of concentration, actually I'm saying I need to put into the rational formula a rainfall intensity which corresponds to a given energetic level. And this is the way the rational formula accounts for energy balance. It's interesting, I think, this consideration, because if you want to understand what you're doing in understanding climate change, energy plays a relevant component. You cannot only consider mass. 1 degree of increase of temperature at the global level means a lot of more energy in the atmosphere. So you have to wonder where this energy ends up. We know that, for instance, probably it ends up in more intensive short rainfall, because we know that the long rainfall doesn't change much. So our assumption is then we assume that it's the low intensity rainfall that is increased, which means that if you have the same value of annual rainfall, if you have more intensive short-term events, you have more dry days. So it means that the peaks are increased and the lows are increased. So this is the reasoning that we make to postulate, on the one hand, that probably rainfall with high intensity is increased. On the other hand, this is the reasoning that we use to build climate models. So it is extremely important that we get the physics of what we are doing, even if we are only making a technical application. Because in this way, as engineers, we gain means to evaluate the correctness, the goodness of our results. Okay. Let's go back here. And this consideration, which I made in like 10 minutes, it's summarized by these 3 lines. Okay, very good. Do you have any question? Okay. No questions. And if you are interested in getting more information, let me just open a Google page with a rational formula for flood estimation. You get a lot of more details. And for instance, this is a PDF. I think it looks like a technical report from the US. The rational formula is widely used. Despite its simplicity, it's widely used for estimating flood risk. And you understand its potential use for estimating climate change impact. You increase 10% rainfall intensity in the rational formula under climate change, and then you get an increase, a corresponding increase of 10% in the river flow. This is linearity. This is equivalence of the probability distributions. We know that it is basically incorrect. On the other hand, it is widely used. Why? Because it's simple and robust. It gives you an estimate which may be not so precise, but it's not completely wrong. Therefore, it's extremely important. And it is also important if you want to get an order of magnitude. Sometimes in my professional meaning research consultancy activity, I am asked in front of a river, what could be the flood flow for this river? So then in my mind, I apply the rational formula. I put a runoff coefficient of 0.8, and I know more or less what is the time of concentration, because you get some sensitivity to it. So if it is a small creek, half an hour rather than a couple of hours. And then I know more or less what is an intense rainfall, an intensive rainfall over a river. And then I just ask for the area of the catchment, and this is fine. There are several links, and let's look also for the videos. You see here there is on YouTube peak discharge using the rational method, and of course you may find, if you look for information, and several lectures, you see. And if you look at these videos, this information, you may find more details with respect to what I'm doing. Okay, now let me open an Excel sheet to give you a very simple example of application. And let me get it. 1 second. I need an Excel sheet, and it is an application which I'm just developing now. So it's interesting because I don't know what comes out, but let's see. Here it is. So let me expand so you can see. Okay, let's refer to a given river, like for which I have some information. So the Sekia River is close by here. Sekia River. A is at the closure. It's 1214 square kilometers. C, let's take it like, okay, let's take 0.8. I think we are a bit overestimating here. And rainfall intensity, I. The Sekia River has a time of concentration. Let me write it here. TC is equal to, it's about 12 hours. So rainfall event I equal for a duration of 12 hours and a duration of 12 hours and a return period of 100 years. Let's take 100 years. Let's write here T equal 100 years. Now, this is the most difficult question. 12 hours. Let me think of it. I think it may be something like 150 millimeters. I don't know. Let's see. 120. This is the most difficult question because 12 hours, I think for 1 hour rainfall over the Secchia River, I would have said like 60 millimeters. But then if you increase the duration to 12 hours, you have to, okay, let's try with 120. The nice thing is that I have already an estimate of Q, which was computed with Q equal, this is what, oh, sorry, this is what I am expecting. I am expecting something like 800 cubic meters per second. Okay, so first of all, let's apply the rational formula in the current condition. And here I have to be very careful of the units because the units must be coherent. If I want to get the result of Q in cubic meters per second, I have to convert the area of the catchment in square meters. And the rainfall intensity, intensity is expressed in millimeters. Here I made a mistake. And intensity is length divided by time. So this is millimeters. Let's put it here. Just 1 second. Okay, F2 millimeters divided by 12 hours. Okay, this is the unit. So I have to convert this rainfall intensity in meter divided by second. Okay. So let's first of all make the conversion. So the area of the catchment is in square meters is the area in square kilometers time 1 million. Okay, because in a square kilometer, it's in a square kilometer there is 1 million of square meters. Good. Time of concentration 12 hours. I need to take the value of 12 in seconds. I have to multiply by 3,600. I don't need to convert the return period because it's not used in the formula. What I need to convert is 120, it's millimeters. I want to express it in meters, so I have to divide by 1000, but then it's millimeters in 12 hours, which means that I have to divide again this value by the 12 hours expressed in seconds. I think this is the resulting rainfall intensity. Okay, what I did, these unit conversion are the most frequent source of error in technical applications. So be very careful, because when you do, I hope I was correct, but I'm not really sure. So I'll check later on. Be very careful, because in technical application, it happens quite frequently that we can make a mistake. It's just a moment to make a mistake. And if you make a mistake, it's really ridiculous, because, if we get wrong in a very complex elaboration, then we are a bit justified. If we get wrong with a very simple calculation, it's really ridiculous. And there is one nice thing of this kind of errors, that they can be easily detected. So the way I check against these errors is to look at the final result. If the final result is comparable to my expectation, then this is fine. If the final result is 3 orders of magnitude different from my expectation, I made a mistake. And this clarifies why it's extremely important that you get a preliminary idea of what you are studying about, a preliminary expectation of your result. In this case, I put it here, up here, and I am lucky that, I know the river, but in any case, even if I didn't know the river, I look at the area and I gain a preliminary expectation. What I put here is extremely important, okay? My preliminary expectation. Okay, good. Now, let's compute Q here then. So Q is equal to plus C plus E, sorry, something went wrong, plus C times E times area here. So now we press return and see what happens. Okay, it's much higher than what I was expecting, but not an order of magnitude higher. So I exclude an error in the conversion of units. And then, why it's higher? Probably because the rainfall intensity is too high, and maybe also the runoff coefficient. So let's play with it. Given that this is too high, it means that probably the runoff coefficient, indeed, let's put it to 0.6, is still twice the result that I was expecting. So probably here the problem is indeed the rainfall intensity, which it was too high. So let's put it to 80 and then we are comparable. Now this is the estimate that I was expecting. Why? Because the rational formula is overestimating typically. Typically it ends up with overestimation. Because actually what happens is that the return period of rainfall is not the same as the return period of flow. And therefore, if we adopt a rainfall with a return period of 100 years, typically we are overestimating. But if the overestimation is of this order of magnitude, this is fine. I mean, the computation that I put in yellow, 800, is a quite precise computation. And also there is one thing which I didn't consider here, which is the area reduction factor of rainfall. So this is why probably my estimate of rainfall was wrong, because the area reduction factor for a catchment that is 1,000 square kilometers is important. Okay, once that we got this model working, and what I did, I anticipate. What I did is to tune the uncertain quantities. So what is uncertain here? It's rainfall and C. So I tuned C. In particular, C is a parameter. It's expected to be tuned in order to get a model that provides a reasonable result. Now, this model is ready to make a climate change impact assessment. So how much will increase by 2100 this rainfall intensity? From 80, it may go to something more, like plus 20%. Okay, so let's put 96. And we get a corresponding 20% increase in river flow. On the other hand, now we can consider the limitation of the model and say, okay, but if rainfall becomes more intensive, probably also C is going to increase a little bit. So let's put it to 0.65. And then this is my estimate, okay? From 1300, I went to 1700 cubic meters per second. This is an example of a very simple climate change impact assessment. Of course, I don't have an estimate of uncertainty. So if my previous computation was something like, I put it here, previous, it was something like 1350. And then the delta is plus this minus this. So this change in river flow, what is the uncertainty? This is my expectation from the model, but what is the uncertainty? Now the reasoning becomes more complicated, and I anticipate that we may find probabilistic methods to estimate uncertainty. We are not discussing them here, or we may go with a Bayesian approach, like plus minus 20%. Okay, so any question on this application? As you see, it's extremely simple, but it requires a lot of reasoning. And therefore, be careful because, beware, because in this course, in this subject, as you will see, we are not dealing with complex math. We are not dealing with very tough analytical developments. In this subject, the problem is not the analytical development. In this subject, the problem is the difficulty is to get a perception of what's going on. And when you talk about climate change, this is essential. Unfortunately, the vast majority of the people are concerned by climate change without realizing what it means. This is the difficult part of this subject. You may think that it's boring what I'm doing. You may think that this application is trivial. That's true. It's indeed trivial. On the other hand, you understand that there is behind the whole thing a reasoning where is energy, where is conservation of energy, where is mass balance. It is this reasoning which is not easy to gain. It is this perception of what's going on that is not easy to gain. It is not something that is in a way undermining your probabilities of getting a good exam done, because you know, during an exam this is something that cannot be evaluated in detail. So even if you don't fully get the concept behind it, I think you can get a good mark in the exam. But I tell you, if you want to become a leader in innovation in climate change adaptation, if you don't get the concept, then the task becomes very challenging. There are a lot of experts around who just talk about climate change without proposing any technical solution to avoid the problem in the short and long term. If you want to become a leader in technical solutions, you need to get the concept. Okay. Now, let's move forward. We have about half an hour. Yeah, please move. Yeah.
Why did you say that um, the uncertainty of the flow would be more or less 20%?
Yeah. Okay. This is a very good question. Okay, I said more or less 20% because this is the order of magnitude of the uncertainty that you may expect in hydrology when estimating peak flow. Actually, it is a kind of expert knowledge, of guess based on expert knowledge. And there are several examples of these assumptions for which I can't really provide a rational motivation, a conceptual motivation. They are just derived on the basis of several applications and suggested by technicians. For instance, one other example that I may provide to you. I spoke with several policymakers regarding climate change, like not really policymaker, like they are technical managers, like managers of water boards, managers of irrigation consortium. And when they have to guess a future change in flood risk or water resources availability, they usually say, let's assume that it's plus 20% under climate change. There is no motivation for that, but this suggestion, you can find this suggestion at the international level. At the international level, I experienced several people by saying, okay, if we don't have a clear idea of what climate will be in the future, let's assume plus or minus 20%. And this is an expert knowledge that is based on the consideration of the uncertainty that we have in our computations. So we know that in our computation also the uncertainty in the best case is about plus minus 20% in the best case, because actually in hydrology in several cases is much higher. And therefore this is why I said, okay, this is my delta, and 400, if I don't have any other information, let's take plus minus 20%. But it is important that you get that it is not a quantitative suggestion. If you have the means for estimating uncertainty, and in most of the cases you have the means, you should make a more quantitative assessment. I'm not sure if I replied to your question, because the reply is basically, it's a guess. Minus 20% was a guess, or plus 20%. Let me just take this opportunity to talk once again about uncertainty. Unfortunately, estimating uncertainty in Earth system modeling is a tough task. And it's a tough task for several reasons, and the lack of information is the main reason. But there is also another reason, which is a kind of limitation in accepting to apply the concept of probability to uncertainty estimation. And I think this limitation comes from the fact that the average preparation of technicians in probability is low. And there are several reasons for this. And probably the most important reason is that probability is not taught in an exciting way, because I don't think that the reason is the complexity of probability. I think the reason is that probability looks boring, and therefore students, this is also my feeling. When I was a student, I had the feeling that it was boring, and then I didn't really like to study it. When I realized that it was really needed, then I made an effort. But I was already more than 30 years old when I realized that I really needed it if I wanted to understand climate change. And so this also explains why I am making an effort to educate you on probability by adopting an approach that is not very formal, because I hope that I get to target without instilling the feeling in you that probability is useless or not needed. And I think this is the reason why estimating uncertainty is difficult. And it's also a cultural reason. And keep in mind that the cultural attitude of a population is very effective on the relationship between the population and the environment, the Earth system. So it is also the kind of organization of the community, dictatorship rather than democracy, has a strong influence on the use of resources and the relationship between humans and environment. So this is something that you may not believe, like what's the problem if we forget about probability? On the other hand, I can tell you that in most of the cases, I could really touch with my hands that the attitude of rejecting methods is also rejecting or applying methods is strictly related to the education of the persons who take decisions. So if the persons have been educated in probabilistic term, it's more unlikely that they reject a probabilistic method. If the persons have been educated under the umbrella of determinism and deductive approaches, only deductive approaches, it's more likely. And I can tell you this is really, it's really effective in the long term. Okay, but this is philosophy. So let's go back to our analytical development. I want to give you Other questions? Good. I want to give you, but this question was really good, really good one. I want to give you another example of another rainfall runoff model. I think this is the last one because I had a third example which I decided to not to include. This additional example requires a very easy mathematical development, and so I am including the example because it allows to get more in depth into the concept of energy balance and mass conservation, concepts that if you want to describe the Earth system are extremely important. On the other hand, it's also an opportunity to see an analytical development with more detail in order to prove to you that indeed, if you want to increase the complexity of our deductive approaches, there is ample room. And indeed, I'm providing two very simple examples, but when it comes to the applications, you have to be fully aware that there are several models, even for describing the single process of rainfall runoff, which, by the way, in climate change impact assessment is very important. But there are several models, and we are limiting our attention to just two river flow models. And there are groundwater models, there are coastal models for coastal flooding, there are ocean models for determining the evolution of the ocean. There are quality models, water quality models, ocean quality models. There are several of them. So there are several models that can be used for impact assessment. If it happens to you that you are called into play and to assess the impact of climate change on a given process, the first thing that you have to do is to get an idea of the literature. Which is not easy because, when we work, we don't have enough time very frequently. But on the other hand, during your studies, it's important that you get oriented so to make your research of the literature easier. Okay, so let's focus on this second model. This second model is called the linear reservoir. It's more refined with respect to the rational formula. The rational formula was conceived for describing the peak flow only, and the linear reservoir describes potentially an entire hydrograph. What is the hydrograph? Okay, let's go back to a Google page. So Google hydrograph. I think there is a Wikipedia page. So let's see, Wikipedia hydrograph, Wikipedia. Here it is. Okay, let's look here. What is an hydrograph? An hydrograph is a graph of river flow. Stream flow is a synonym for river flow. You see cubic meters per second a long time. This is the Julian day. This is an hydrograph. Here is another hydrograph. You see here it's in Spanish, but you have in blue the rainfall, and in red the river flow. Caudal is river flow in Spanish, and lluvia is rainfall. Probably you know Spanish better than me. I just know a couple of words. And then there is the time in the horizontal axis. So this is, you see that there are two scales, one for the river flow and one for the rainfall here. And the rainfall is given in millimeters. There is always this problem of unit conversion. So, and you see the river flow here is given in cubic meters per second, which is the usual unit that is we use for rivers. But when we talk about flow in water supply system, usually we talk about liters per second, not cubic meters. So liters per second, you need a conversion to pass to cubic meters. It's extremely boring. Okay, this is something not relevant. Let's go back. So the hydrograph is a graph showing the rate of flow, discharge. Discharge is synonym of stream flow and river flow. versus time past a specific point in a river channel or conduit carrying flow. Okay, so the rational formula, the linear reservoir, sorry, it's can reproduce the whole hydrograph. How does it work? Let me just open another graphic window because it is very simple. It's a very clever idea. So let's see. No, this is not good. Just 1 second. It's not good because it's too small. So file. Let me first of all change the background color. File, new. And so let's take with something like 2000 and height, let's say 1000. Okay, good. So what is the idea of the linear reservoir? The linear reservoir is, first of all, we refer again to a river, and the river is 1 second because I need to okay, here it is. I need to get a less wide line. Let me see. Okay, this is fine. And let me take the black for now. Okay, the river is assimilated to a tank, like, just 1 second, let me move here, is assimilated to a tank, like just in this case. This is our river, is assimilated to a tank, and we assume that in this tank, we get a rainfall that comes in. Let's call it with the symbol rainfall intensity. I go back to the web page to see the symbol P. It's PT. I'm writing with the mouse, so be patient. It's not very good, but it's simple, so I think you understand. So we have the rainfall PT that goes into the river, and the outlet of the river is assimilated to a hole in the bottom of this tank. So here we have our outlet. Just 1 second. Now it's okay in black here. Here we have our outlet. Good. And we assume that into the river there is a storage of water, because of course in the body of the river we have a storage of water, and the level of this storage, let's call it W. This is W. W depends on time because it's changing in time. So here we have time. Good. And here we have from the bottom discharge, we have our outflow. So here we have our outflow, which we call QT. Good. Now, so this is what we call a conceptual model. So we assimilate the river to a simple system. Actually, I use the term river, but it would be more correct to say that we assimilate the catchment to a tank. The whole catchment, because the water storage is not only into the body of the river, it's also on the hill slopes, it's over the trees, etc. Let's assume that the rainfall that comes into here, it's net rainfall. So it's net rainfall. What does it mean, net? It means that losses have been already removed. So losses removed. Perfect. So this is net rainfall. That's fine. Now, how can we describe the functioning of this system? First of all, the simple system, it's a reasonable approximation for a river. There is rainfall coming over the catchment. which contributes to creating a storage, and then we have the outflow from the river mouth, which is originating the river flow. Now, in this simple system, we may apply a mass balance equation. We may say that the rainfall intensity minus river flow is equivalent to the change of storage. And this is precisely what we find here. Sorry, here. Rainfall minus rainfall PT minus QT is equivalent to the change over time of WT. This is a differential equation, okay, because it's an equation that describes the change in storage. In order, if we want to describe the storage, if we are interested in describing the storage, then we need to integrate this equation, okay, perfect. Now, here, let's focus only on the first equation here. We have a known, which is rainfall. We assume that rainfall precipitation, we know it. But we have two unknowns here. One is storage, left-hand side, and the other one is river flow, which is what we want to describe. Good. Now we need a second equation. And it is fine because we may remember that we didn't use yet the energy balance. So the second equation that we introduce must be an equation relating the two unknowns between them. And therefore an equation which either gives the value of an unknown or a relationship between them. And if we think at a logical equation, it may be indeed an equation that relates the river flow to storage, relates QT to W. Because the more the storage, the more the river flow, it's clear. And then the idea was at the beginning to use a simple linear relationship. This is why it's called the linear reservoir. You see here a linear relationship between the volume and the river flow Q, the volume W and the river flow Q. This linear relationship, it's an assumption. It's in general, it's not linear, this relationship, but we can assume it's linear. It's an assumption. And however, we can recognize here an energy relationship because we are describing flow, which is originated by the energy given by storage. So this is an energy equation. Okay. Now we have two equations. One is a differential equation and two unknowns. So the system is solvable. The system is solvable, even if probably we will need an integration. Okay, so let's, before I move forward, let's observe that K is a constant, it's a parameter. Like C, it's a parameter, it's a constant that is not related to time here and has the dimension of a time. Very good. How can we combine these two relationships? It's quite easy. We can take the derivative of the first relationship, the second relationship, and plug into the first relationship. So we can take the derivative of W from the second relationship and plug into the left-hand side of the first equation, which is what we find here. K dq to the t, K is a constant. So when you get the derivative, it keeps, we can keep it unchanged. The q to the t is equal to pt minus qt. And here we see that indeed, in order to derive the final value for q, a long time, we need to make an integral. How can we make this integral? Please remember this development, because this is one of the few quantitative analytical questions that I may ask you at the exam. So if you are able to make this simple development, it's hopefully there is a mutual satisfaction of me and you. So the way to integrate this relationship is first to multiply both sides by this quantity e to the power of t divided by k, and dividing each member by k. So if you look, for instance, at the first term, it is derived by multiplying the q over the t. We multiply it by e to the power of t over k and divide by k, so the k that is in the above equation disappears. Okay, good. Now there is the second term, which is the qt term multiplied by e to the power of t over k divided by k, and then we have the last term, which refers to rainfall. Good. Now, why we multiplied everything by e to the power of t over k? Because this relationship you can see above in the screen now can be written in this simple way, because we recognize that the first two terms here in the above equation are nothing else than the derivative with respect to time of the product between e to the power of t over k and qt. You see that if you take the derivative of this product, you get the first two addendum at the above the equation. And then we bring at the right hand side the term related to rainfall. Good. At this stage, we can integrate. If we integrate this relationship, you see here, we just integrate between 0 and t, both terms. I just added in the second equation the integral sign. Okay. Now, of course, in the left-hand term, there is the integral of just one second, because I think here there is a mistake here. There is something missing, which is something I was expecting, because I rewrote these equations. So here I am forgetting the derivative, the sign of derivative here. And because in the left-hand side, at this level, second equation, I should have the integral of a derivative, which gives back just the argument of the derivative here. In the right hand side, you have instead the integral that is kept, but there is an arrangement to be made here, and I will correct the equation ASAP as soon as possible. So within a couple of hours, you will find the correct equation here. And then from this corrected version, it is easy with some intermediate steps to get to this final expression. Okay. So just please have a look later on at this web page with the correct version, and understand please how from the version that will be corrected we get to this version here, which is now above in the screen. It is an integral which we usually integrate numerically, but it is interesting to look at the case where P rainfall is constant in time, because when P is constant in time, we can get an explicit expression for the river flow. Let's see what happens. If you get P constant, you can bring out P divided by K, the two constants, out of the integral sign. You see here is P divided by K, integral between 0 and T of this quantity. Which can be written in this way. It can be written, the integral of this quantity can be written in the form of the second equation that you see here, because keep in mind that the factor e to the power of minus t divided by k is constant. So you can bring it out of the integral, okay? And then it remains the very simple integral that you see here, which can be written in this way, computed by 0 and t. And then you get this final relationship here, which can be simplified in the form of the last equation. Remember, this is constant rainfall. So if we assume that at the time 0, the river flow is 0, the hydrograph that we get is this one, for constant rainfall. So what does this graph say? And one question of the exam may be, can you please draw an hydrograph from the linear reservoir with constant rainfall? What I am expecting is this hydrograph here. Remember that rainfall is net rainfall. So what we get is that we start from 0 with the hydrograph, which is perfect. And then asymptotically, the river flow reaches the intensity of rainfall. There is one thing that I forgot to say at the beginning. Let me go back to this graph. This is actually PT. It's not only PT, I write it here. This is PT times K. This is something I forgot to say at the beginning. Okay, so just be aware of that. This is not rainfall intensity, is rainfall volume per unit time over the river, over the catchment. Okay, so there is the area of the catchment here. I realized it now, because if you look at the final graph, of course, the river flow cannot be given only by rainfall intensity. It must be given by rainfall intensity times the area of the catchment. Okay, and it is written on the web page that P is rainfall volume. Let me see, just I check, and let's see. Where WP is rainfall. No, I think I need to specify it. I will also make the change here. Be patient, it's a new lecture, so you have to bear with me. Okay, so this is the hydrograph. Now, the question here is the value of K. Okay, and the value of K, let's discuss it next time. And because next time I want to discuss, as I anticipated to you, how the model parameters for a given model, maybe a climate model, maybe whatever, are estimated. So let's forget about the value of K. What I want to say, just to conclude today, is that the linear reservoir, which is based on this very simple scheme, can be made more complicated, more complex. And for instance, you may describe the outflow in a different way. So now we adopted for the outflow the very simple relationship QT is equal to WT divided by K. This is our very simple relationship. you may use more complicated relationship. There is no limitation to our creativity. The only thing is that we have to build something that is consistent, that is physically plausible, physically correct. We have to be careful because, I mean, creativity allows us to build more complex models, which is fine, more detailed models, which is fine. On the other hand, we have to make sure that the results that we get are good results. So when you decide to adopt a more complex model, make sure that the model is tested, that the model is providing a good representation of the system. And I give you an example here, and I close with this. This is taken from Wikipedia. This is a more complicated conceptual scheme, which is non-linear. There are several discharges. This is reasonable. You may assume that the river flow is given by the sum of several discharges instead of only just one. And in doing that, you introduce complexity in the form of non-linearity. Why? Because, you know, if you have a second discharge, it becomes activated only when the water level, the blue line into the tank, reaches the level of the discharge. And therefore, there is a threshold effect. There is a tipping point. This tipping point is clearly something non-linear. The discharge doesn't depend linearly on the storage. It's a dependence that vary depending on these thresholds. This is on the one hand fine, non-linearity is a good solution. On the other hand, beware, as I said, of the representativity of the approach that you use. And with that, I would say that give me 30 seconds. We discussed inductive versus deductive approaches. What is best? There is no unique answer, like there is not unique answer to the impact of climate change over a specific context. There is no unique answer because depending on data availability, depending on the kind of impact that you are studying, depending also on the resources that you have at hand and the time that is given to you to complete your task, it may be preferable to use one approach rather than the other one. What is, in my opinion, necessary is that you get an overall picture of the possibilities, an overall picture of the approaches, and then you can decide, basing on your time, basing on the constraints, basing on the data, what is the best one. At the end of the story, you may always apply both of them and take the more conservative approach if this turns out to be a solution that is advisable. But everything should start, as I said before, from the knowledge of the methods. Like for probability or determinism, we need to know both. And then with an unbiased evaluation and a very relaxing, let me say, evaluation, we can decide what is the best method. And you know, the relax is an important component because when we don't know something, we get nervous. And in order to deal with climate change, instead, we have to avoid a nervous approach. Okay, now let me say once again, I am correcting these equations quickly and then try to understand the development. It's a very simple integration. Do you have any questions? Let me share the screen. Before we say goodbye, I want to stop the recording.